Good morning. Today we are going to talk about applied conformal field theory of Ising model on torus, and this is going to be the basic outline what we are going to discuss today. I'm going to start with classical Ising model. This is for you to get familiarized with what I mean by the critical exponent, and then we are going to map this classical Ising model to its quantum cousin, and then it will be followed by some smart transformation which will map this quantumizing model to a free fermionic theory. Then we are going to exploit the symmetries of the fermionic theory to extract the critical exponents. So let's get started with classical Ising model. The classical Ising model is described on lattice where each point has spin, and this spin can either take up direction or down direction. This spin can interact with its nearest neighbor and external field, and when we have the periodic boundary condition, we can describe this lattice on torus. So let's revise our statistical mechanics. We can write the partition function for the Ising model, and from this partition function we can also write the free energy. Once we have the free energy, we can write various kind of measurable thermodynamic quantities such as magnetization and magnetic susceptibility. There is a rule, susceptibility sum rule, which tells you that we can write the susceptibility in terms of spin-spin correlation function. And when we have the translation symmetry in our system, then we can write susceptibility like this. So I plotted the magnetization with the graph of magnetization with temperature, and I got this. So below a certain temperature known as critical temperature, the magnetization is non-zero. All the spin are trying to align in one direction, and above the critical temperature the system is in disorder phase, which means that each spin is aligned in random direction, and the average is 0. Below the critical temperature, the magnetization goes like Tc minus 3 raised to power beta. This beta is one of the critical exponent, and there are 6 critical exponents: alpha, beta, gamma, delta, nu, eta. So there's one interesting thing about this, that this critical exponents are not independent. We can write all the 6 of them in terms of only 2. So this is followed from renormalized group theory. Okay, now what I'm going to do is I'm going to map the classical Ising model to its quantum cousin. I'm not going to give the sophisticated maths behind all that. For that you can refer to my term paper. Instead, I am going to give you some argument which will convince you to accept the correspondence. In general, it is possible to map t plus 1 dimensional classical Ising model to t-dimensional quantum Ising model, and the Hamiltonian for these systems are given like this. And I want you to focus on quantumizing Hamiltonian. You can see the external field here plays a role, whereas this is absent in classical Ising Hamiltonian. So this G in the quantumizing Hamiltonian is known as coupling parameter, and this G in the asymptotic limit is a linear function of temperature. What we saw in classical Ising model was when we were below the critical temperature, the system was in order phase, which means that all the spin were trying to align in one direction and the magnetization was non-zero. Whereas what we see in the quantumizing model, when coupling parameter is very small, all the spin try to align in either spin up or spin down direction. In classical Ising model, we saw when we were above the critical temperature, all the spin were arranged in random direction and the magnetization was 0. Whereas what happens in quantumizing model, when coupling parameter G is very large, all the spin try to align in Sx plus direction. And from quantum mechanics we know that if I'm going to measure Sz for Sx plus spin, there's equal probability of finding Sz plus and Sz minus, which leads to magnetization 0. So this is the picture of what I have said so far. When in classical Ising model, when system was in order phase, which means when we were below the critical temperature, the spins were tend to align in one direction, and whereas when we were in disorder phase, when we were above the critical temperature, the spins were aligned randomly. Whereas in quantumizing model, when the coupling parameter is very small, the spin try to align in one direction, either spin up or spin down. And when this coupling parameter is very large, all the spin try to align in positive x direction, which leads to magnetization 0. Now we are one step away from the interesting part of our talk. Before that, we have to map the quantumizing model to free fermionic theory. This will be followed from the series of smart transformation. First, we have to identify fermionic creation and annihilation operator, which follow the anti-commutation relation given like this. And if I define raising a lowering operator in terms of sigma x and sigma y polymatrices, then which also follows the commutation relation similar to the fermionic creation and annihilation operator, we are tempted to identify lowering and raising operator as creation and annihilation operator. But wait, this has a problem. The problem is the fermionic operators anti-commute at different sites, whereas the raising and lowering operators decommute at different sites. So to remedy this problem, we perform Jordan-Wigner transformation, which recovers the true fermionic commutation relation, and we can invert this and write in terms of creation and annihilation operators. So lowering operator acts on spin up and make it spin down, and raising operator acts on spin down and make it spin up. If I identify up state as a whole and down state as a particle, then we can identify a lowering operator as creation operator and raising operator as annihilation operator. So this is the intuitive picture of what we do in Jordan-Wigner transformation. So what we have done so far, we have mapped spin half degree of freedom to spin less degree of freedom, where particles are hopping on a ring. Now to simplify the algebra further, we are going to rotate a spin axis by angle of pi by 2 and substitute the sigma x and sigma z in quantumizing Hamiltonian, and what we get is this, where the particle number is not conserved. So we are going to diagonalize this Hamiltonian, so we can go to fermionic basis where particle number will be conserved. Before that, we are going to perform Fourier transformation of this Hamiltonian, and if I define fermionic operator gamma k like this, where this expression follow this property, then and the gamma k follows the anti-commutation relation which we expect from any fermionic creation and annihilation operator. And if we with our choice of uk and vk like this, and we substitute this in Fourier transform Hamiltonian, what we get is this Marinoff fermion Hamiltonian, where particle number is conserved. So in continuum limit, we are going to replace the Kronecker delta with Dirac delta, and when we substitute this in the Hamiltonian, we get Hamiltonian for Marinoff fermion in the continuum limit like this, where delta is like mass term, and we saw in quantumizing model that g equal to 1 was the phase boundary between order and disorder phase, and at t equal to 1 this delta is 0. With this mass term vanishing, the Hamiltonian becomes conformally invariant. And what I mean by that we will see in the next step. So conformation transformation are the transformation which preserve the local angle between any two lines. More formally, it is given like this, and it consists of translation, dilation, rotation, spatial conformation transformation, out of which you must be familiar with the translation rotation as part of Poincare group. Now I'm going to give you some definitions. So if I may scale my variable and then my field transform like this, then the field is said to be have conformation dimension HH bar. If I confirm on my conformal transformation z to f of z and field transform like this, then field is said to be a primary field. And when this f belongs to quotienting special linear group with z2, then field is said to be quasi-primary field. So if my 2-point function is invariant under the translation, then we restrict our 2-point function like this. And if my 2-point function is invariant under the scaling, then my 2-point function is given like this. And if my 2-point function is invariant under the spatial conformation transformation, then the 2-point function is given like this. So this was the 2-point function for quasi-primary field. For general field, the 2-point function is given like this with field h plus h bar. If we make correspondence of the spin correlation function and 2-point function by introducing twist field, whose dimension, conformation dimension HH bar are 1 by 16 and 1 by 16, and if we substitute this HH bar in the expression of 2-point function, then we get 2-point function going like 1 by r raised to power 1 by 4. And if I compare this 1 by 4 with the Onsager's value, then so this matches with the Onsager's value. We saw the application of conformal field theory on the statistical mechanical Ising model of ferromagnetism highlights the connection between the phenomena near criticality and the quantum field theory, in particular the model of free Majorana fermion. We started from a classical Ising model and mapped it to its quantum equivalent. A series of transformations lead to Hamiltonian, whose mathematical structure will link to that of Majorana fermions. The symmetry of the derived Hamiltonian, and in particular formal invariance, was exploited to extract the value of critical exponent of physical quantity, which in our case was eta, pertaining to the connected correlation function. However, we need to find one more critical exponent to complete the theory near the criticality, which remains open for others to explore. Aforementioned, we can express all the 6 critical exponents in terms of 2 critical exponents. Thank you for attention. Any questions?